to apply this in chemistry is through processes like chemical reactions, okay? And so if you think about what the final part of a chemical reaction is versus the initial part, hopefully you can figure out that instead of final, we can put the final part of a reaction, which are the products, good. We can do the enthalpy of the products instead of just generic final minus the initial part of a reaction, which is, good, reactants, minus the enthalpy of the reactants. And that will be equal to Q if we're talking about a chemical reaction, okay? So this would just be for chemical reactions. And so we usually label that as delta H with a little Rxn there for meaning the change in enthalpy for a reaction. That's just going to be equal to the enthalpy of the products minus the enthalpy of the reactants, final minus initial, and it's still going to be equal to Q. Okay, so let's do a problem where we use this in a chemical reaction so you can actually see it being applied. Again, don't think of enthalpy or change in enthalpy as anything other than just heat. Okay, that's all we are going to use it for. So delta H equals Q. All right. Now, let's do the combustion of propane. Okay, so take a minute, just pause the video for a second. I want you to write a balanced chemical reaction for propane. Combusting. Propane. Combusting. Ready? Go. Okay, good. So that's C3H8. We are combusting, so that means reacting with oxygen. Our products, as always, are carbon dioxide and water. Let's balance this with a 3 here, a 4 here. We have 6 oxygens plus 4. That's 10, so we will need a 5 there. Hopefully that's what you got. Now, you can look up the delta H for this reaction, okay? And if you look, you can look them up in tables. There's lots and lots and lots of tables that just literally list the change in enthalpy of reactions for every reaction. And you can find that for this reaction, this delta H value will be negative 2220 kilojoules per mole of propane. Okay? So let's think about what that actually means. If you can remember, do you guys remember how to put like one of these balanced chemical reactions just in like sentence form? Okay, we've done this a lot, tried to drive this home, but in case you don't remember, it would be something like this. 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of CO2 and 4 moles of water. All right, that's like what the balanced chemical reaction actually means. This delta H of the reaction is just telling us how much energy in this case is released, because it's negative. This much energy is released for every 1 mole of propane that you react. So luckily, this is just a 1 out here. But if this were another coefficient, let's say this was a 2 here when we balanced it, just theoretically. Well, then this delta H of the reaction, in order to be applied to this reaction, because now it's 2 moles of C3H8, you would just do the same thing to our delta H of the reaction. You would just multiply it by 2 to be able to apply it to this chemical reaction. But nicely enough, it is just a 1, so this will hold for our reaction. Now, if we wanted to kind of put it in to our chemical equation as like a reactant or product, can you think about first what type of process this delta H being negative would, what it would mean? Would it be an exothermic or an endothermic reaction? Meaning that this is a negative amount of heat. Good, it would be exothermic, right? So if you think about that, that means heat's being released. Where would you put that? Would you put that as a reactant? Would you think of heat as being a reactant going into the reaction? Or would you think about it as a product, the heat coming out of the reaction? Hopefully you see that it would actually be considered basically a product, right? So we could actually just write this as a product and just put plus 2220 kilojoules at the end of our balanced chemical reaction because it's being released with the products. If it was an endothermic reaction, it would be considered a reactant. So you could actually list it there with the reactants. Okay? But most of the time, you're just going to see it listed as kind of a delta H for the reaction. It's not going to be put into the balanced chemical reaction, but you can absolutely think about it as either a reactant if it's endothermic or a product if it's exothermic. Okay? So let's see how we would do a problem. Let's say we have, 25 grams of propane that combusts. Let's calculate delta H for this reaction. Okay? So we have 25 grams combusting. Remember what this number means, okay? It's 2220 kilojoules for every 1 mole of propane that reacts. Well, we have 25 grams. We don't know if we have exactly 1 mole, so we have to figure that out. You guys should know by now that we can very simply go from grams of propane to moles of propane just using the molar mass. So let's add that up. It's 12 times 3 plus 8, 44 grams is 1 mole of propane. And we want to get the delta H, the heat released for this process. And so we can use this delta H of the reaction as kind of another conversion factor, right? Look, we have units of kilojoules and moles of C3H8. Well, in our little train fraction here, we are at the unit of moles of C3H8. Now we have to cancel that. We're trying to get to kilojoules. So we can actually just plug this value, this delta H for the reaction. Computer cut off. But as I was saying, we can just plug that delta H for the reaction in as a conversion factor. So it'll be negative 2220 kilojoules in the numerator over 1 mole of C3H8, because that's what it says in our delta H for the reaction. If you notice, look at the units, grams of propane cancels, moles of propane cancels, and we are left with kilojoules. Kilojoules is our unit of heat. Heat is delta H. So we can stop right there and calculate it. So it'll be 25 divided by 44 times negative 2220. And we get, let's see, we want 2 sig figs. So negative 1,300 kilojoules would be our answer. This chemistry lecture series brought to you by Rainy Weekdays. It's easy to stay inside during rainy weekdays.